IP routing methods. IP network routing is the process of selecting the best path for IP packets to travel across different networks from a source to a destination, handled by specialized devices called routers that use routing tables and routing protocols, like OSPF, BGP, to intelligently forward data, ensuring efficient and reliable communication on the internet and other IP-based networks. It's like postal service, where routers act as sorting centers, directing mail, packets, closer and closer to its final address using the most efficient route available. How it works, the basics. 1. Packet creation. A device creates an IP packet with source and destination IP addresses. 2. Default gateway. If the destination is on a different network, the source device sends the packet to its default gateway, a router. 3. Router examination. The router receives the packet, strips off the layer 2 info, like Ethernet, and examines the destination IP address in the layer 3 header. 4. Routing table lookup. The router consults its routing table to find the best next hop, the next router or directly connected network. 5. Forwarding. The packet is sent out the appropriate interface towards the next hop. 6. Repeat. This process repeats across multiple routers until the packet reaches the destination network. Key components and concepts. Routers, hardware devices that make routing decisions. Routing tables, databases on routers listing network paths, populated by static configuration or dynamic protocols. Routing protocols, algorithms, like OSPF for internal networks, BGP for the internet, that routers use to share network information and build tables. IP, Internet Protocol operates at layer 3, network layer, of the OSI model, providing logical addressing, IP addresses, for devices. Why it's important. Interconnectivity, enables communication between different networks, example your home network and a server across the world. Efficiency, finds the most optimal path, balancing factors like speed, load, and reliability. Scalability, manages complex global networks like the internet. IP network routing is the process of selecting paths across one or more networks to transmit data packets from a source to a destination. This function occurs at layer 3, network layer, of the OSI model, primarily using specialized hardware called routers. Core mechanisms of IP routing. Routing table, a database stored in a router's RAM containing a list of known network destinations, the interface to reach them, and the next hop address. Packet inspection, when a packet arrives, the router examines its destination IP address in the IP header. The longest match rule, if multiple entries in the routing table match a destination, the router selects the most specific one, the one with the longest subnet mask. Default gateway, if a router cannot find a specific match for a packet's destination, it sends the packet to a pre-configured default route, often 0.0.0.0/0. Types of routing. Type description. Best for static routes are manually entered by an administrator. Small, stable networks with routing and do not change automatically. Predictable paths. Dynamic routers use protocols to automatically discover large, complex networks that need routing paths and update their tables in real time. To adapt to link failures. Default a catch-all route used when no specific path is stub. Networks with only one exit routing found in the routing table. Point to the internet. Key routing protocols. RIP, Routing Information Protocol, a simple protocol that uses hop count, number of routers, to find the shortest path. OSPF, Open Shortest Path. First, a widely used interior protocol that builds a complete map of the network to find the fastest path. BGP, Border Gateway Protocol, the standard protocol for the global internet, used to route traffic between different large organizations or autonomous systems, as iGroup, a Cisco proprietary hybrid protocol that combines features of both distance vector and link state algorithms. Importance and benefits. Scalability, allows networks to grow by automatically discovering new segments. Resilience, if one path fails, dynamic routing automatically finds an alternative to prevent downtime. Efficiency, optimizes traffic by selecting paths based on bandwidth, delay, or cost metrics. Quality of service, QoS. Modern routers can prioritize latency-sensitive data like voice calls, VoIP, or video streaming. Routing table structure. A routing table is a structured data set maintained by routers to determine where data packets should be sent. It acts as a map of the network, organizing essential delivery instructions into specific fields. 1. Essential fields, the columns. Each entry in a routing table typically consists of these key fields: destination network, the IP address of the target network or host. Subnet mask/prefix, defines the range of IP addresses in the destination network. In modern systems, this is often shown in CIDR notation, example /24. Next hop, gateway, the IP address of the next router in the path toward the destination. Outgoing interface, the specific physical or logical port, example gigabit Ethernet 0/1, through which the packet must leave the router. Metric, a numerical cost value, such as hop count or bandwidth, used to rank routes. Lower metrics indicate more efficient paths. Administrative distance, a rating of the trustworthiness of the route source, Example OSPF versus static. If two protocols provide a route to the same destination, the one with the lower AD is selected. Two types of routes. Routes are categorized by how they were learned, directly connected, networks physically attached to the router's interfaces, these have the highest priority. Static routes, manually entered by an administrator. Dynamic routes, learned automatically through protocols like OSPF, BGP, or iGroup. Default route, a fallback route, marked 0.0.0.0/0, used when no specific match is found for a destination. 3. Internal data structure. While viewed as a table, the internal software implementation is optimized for high-speed searches. Modern routers use advanced data structures like tries, specifically binary or LC tries, or hash tables to achieve longest prefix match, LPM, lookups in microseconds. 4. Routing table, RIB, versus forwarding table, FIB. In high-performance routers, there is a clear separation between the brain and the engine. Routing information base, RIB, the master table containing all known routes and protocol-specific data. Forwarding information base, FIB, a streamlined subset of the RIB that is precompiled and often mirrored in specialized hardware, ASICs, for near-instant packet forwarding. A router determines the best path for a data packet by following a strict, hierarchical decision-making process based on the information stored in its routing table. Step 1. Longest prefix match, LPM. This is the first and most important criterion. The router compares the packet's destination IP address against its routing table entries. If multiple routes match, it selects the one with the longest subnet mask, the most specific path. Example, if a packet is going to 10.1.1.5 and the router has routes for both 10.1.0.0/16 and 10.1.1.0/24, it will always choose the /24 route. Step 2. Administrative distance, AD. If there is a tie in prefix length, multiple routes to the exact same destination network, the router evaluates the trustworthiness of the source. Each source has a pre-assigned AD value, lower is better. Directly connected, 0, most trusted. Static routes, 1 OSPF, 110, example for Cisco. RIP, 120. Step 3, metric, tiebreaker for same protocol. If multiple paths to the same destination are learned via the same protocol, the router uses a metric to find the most efficient route. Lower metrics are preferred. Different protocols use different measurements. RIP uses hop count, number of routers. OSPF uses cost, primarily based on interface bandwidth. iGroup uses a complex formula involving bandwidth, delay, reliability, and load. Summary of priority factor rule. First longest prefix match, most specific route wins, example /24 beat /16. Second administrative distance, most trusted protocol wins, lower value. Third metric, fastest /closest path within a protocol wins, lower value. Equal cost multipath. Fourth, if all above are equal, traffic may be split across multiple paths, ACMP. If no match is found at all, the router sends the packet to the default gateway, 0.0.0.0/0. If no default route exists, the packet is dropped. Routing algorithms are the mathematical formulas used by dynamic routing protocols to calculate the best path for data packets. Modern IP routing in 2025 primarily relies on two major categories of algorithms, with emerging research currently pushing their computational limits. 1. Link state algorithms, shortest path first. These algorithms require every router to have a complete map of the entire network topology. Core algorithm, Dijkstra's algorithm. It calculates the shortest path from a source router, the root, to all other nodes in the network by examining the cost of each link, usually based on bandwidth. Characteristics, provides fast convergence and is loop-free, but requires more CPU and memory to maintain the full network map. Example protocols, OSPF, open shortest path first, and ISIS. 2. Distance vector algorithms. These algorithms are based on routing by rumor, where routers only share their own perspective of the network with immediate neighbors. Core algorithm, Bellman-Ford algorithm. It calculates the distance, metric, and direction, vector, to a destination. Characteristics, simple to configure and low resource usage, but suffers from slow convergence and potential routing loops, example the count to infinity problem. Example protocols, RIP, Routing Information Protocol, and Cisco's iGroup, which uses a hybrid version called the diffusing update algorithm or DUAL. 3. Path vector algorithms used for interdomain routing between large organizations or autonomous systems, as core algorithm. These track the entire path, a list of as numbers, to a destination rather than just the next hop. Example protocol, BGP, Border Gateway Protocol, the protocol that runs the global internet. 4. 2025 advancements in routing. Dijkstra breakthrough. In 2025, researchers from Tsinghua University and Stanford developed a new deterministic algorithm that surpasses the speed of Dijkstra's for finding the shortest path in sparse networks by avoiding traditional sorting barriers. AI-enabled routing. Modern enterprise systems are increasingly integrating machine learning, ML, and deep reinforcement learning, DRL, to predict traffic congestion and adapt routing in real time for better quality of service, QoS. Graph theory innovation. Advanced pathfinding like the A**, algorithm, while common in gaming and GPS navigation, is being adapted for specific high-performance network lookups to find good enough paths more rapidly than traditional exhaustive searches. Beyond standard destination-based routing, modern IP networks in 2025 utilize advanced techniques to handle complex traffic requirements, security, and load distribution. 1. Policy-based routing, PBR. PBR allows network administrators to bypass the standard routing table. While traditional routing only looks at the destination IP, PBR can route traffic based on match criteria, source IP, source/destination ports, protocol types, or packet length. Use cases: directing high-priority business traffic over low-latency links while sending bulk traffic, like backups, over cheaper, high-bandwidth paths. Implementation, typically configured using route maps that identify traffic via access control lists, ACLS, and specify a next hop. 2. Equal cost multipath, ACMP. ACMP is a strategy where a router distributes traffic across multiple best paths that have an identical routing metric. Function, it prevents a single link from becoming a bottleneck by load balancing packets at a per-hop level. Advancements in 2025, modern implementations support weight-based ACMP, allowing administrators to assign weights to different paths to influence traffic distribution. Protocols, supported by most major protocols, including OSPF, BGP, and static routes. 3. Virtual routing and forwarding, VRF. VRF allows multiple independent routing table instances to exist within a single physical router. Isolation, traffic in one VRF cannot see or communicate with traffic in another by default, providing layer 3 network segmentation. Overlapping IPS, because instances are separate, different departments or customers can use identical, overlapping, IP addresses without conflict. VRF Lite, a lighter version used without MPLS backbones, common in 2025 enterprise data centers for isolating management traffic from data planes. 4. Static plus dynamic hybrid routing. A hybrid routing approach combines the predictability of manual configuration with the adaptability of automated protocols. Core concept, a proactive protocol, like OSPF, discovers network topology while a reactive or static element handles specific fixed routes. Common setup, administrators use dynamic routing, OSPF/BGP, for the core network to ensure automatic failover, while applying static routes for stub networks, small branches with only one exit. Floating static routes, a backup static route with a higher administrative distance that only activates if the dynamic protocol fails. 2025 benefit, this combination improves operational performance by replacing complex policies with a single default route where appropriate.